Unit 4, energy. Energy refers to the capacity or the amount that an object performs work. We'll get to the definition of work in a moment, but first there are three predominant types of energy, each with their own equation. Kinetic energy, 1/2 mv squared. That m value is in kilograms, like most masses that we work with. Then you have gravitational potential energy, G refers to the acceleration due to gravity 10. H refers to the height that an object has with reference to 0 meters. And we get to pick what 0 meters is. It could be the ground, or we can pick an arbitrary spot and say, well, this is the ground, this is 0 meters. You also have elastic potential energy, which is equal to 1/2 kx squared. K is the spring constant of whatever spring that you happen to be working with at this time, or rubber band, or whatever stretchy device that we're working with. X squared. X refers to the distance by which the string or spring has been stretched or compressed. And that value will be in meters. It's frequent, just using logic, that we would roll with a lot of springs that have centimeter values, but we convert it into meters. Those are your main three forms of energy that we work with in mechanics-based physics. There are other forms of energy, heat, light, whatnot, but we're mostly working with these three. The main law that governs the majority of Unit 4 is going to be the law of conservation of energy. Now, what this law states is that all of the initial energy of a system is equal to all of the final energy of the system, with no energy loss. An energy that is lost, that we lose out on calculating in physics, is usually lost due to thermal energy or friction. That's the result of the majority of the energy that we lose out on. There are three types of energy that could be in play in both before and after instances: kinetic energy, gravitational potential energy, and elastic potential energy. And a good chunk of this unit is just going through various situations and using these values to determine how much energy is going on in before and after events. Let's do a couple of examples and you'll get the hang of it. This first example, let's do a roller coaster, which is leaving from position A, making its way down to position B, and then rolling back up to position C. We'll say position C is at height reference to H, and we'll call the bottom of this roller coaster track 0 meters. That's what I mean by reference to ground. Are we at the ground? Well, we can call it the ground and say, well, there you have only kinetic energy. You have no more gravitational potential energy there at ground. And let's diagram our energies at positions A, B, and C. In position A, the total energy going on here is only gravitational potential energy. There's no elastic potential energy. I don't see any springs or stretched rubber bands or anything like that. There's no kinetic energy, because we would probably, in questions like this, say, hey, you begin your motion from rest, or use that phrase, from rest, to dictate that there's no initial kinetic energy. Let's do position B. In position B, your only energy is kinetic, with reference to ground. If you tried to add a gravitational potential energy, that H value component of that equation would be 0. So there is no gravitational potential energy at position B. At position C, your total energy is equal to a combination of kinetic and gravitational. Keeping in mind that all of these values are specific for their locations. The kinetic energy at position B, the gravitational potential energy at position A. And the way a lot of these questions work is knowing what we know about the object at position A, how fast are you moving at position C? Well, diagramming that, if we wanted to do that, we would use the law of conservation of energy. Energy initial is equal to energy final. Let's expand that out. Okay, so knowing what we know about where we're at on position A, And knowing that the question's asking about your location at position C, which energies are in play? Well, at position A, you have only gravitational potential energy. At position C, you have a combination of gravitational potential energy and kinetic energy. You can expand these energies out in order to solve for the variable V for kinetic energy at position C. Look, there we go. We can totally solve for the velocity of the object at position C. Another quick example, this time involving springs and elastic potential energy. This spring is horizontally oriented because we don't want gravitational potential energy to be a factor in our easy-go-lucky example. Okay, we have position A, in which our spring is in the rest position or equilibrium position. We have position B, in which we have our spring fully compressed, just holding it there until we're ready to let it loose and let it go rightward. And then position C diagrams a moment at which the spring is still attached to the mass, and we're in motion, and we're experiencing rightward motion here. We have just pulled the pin or whatnot, and now we're experiencing rightward motion. Let's diagram all of our energies for positions A, B, and C. For position A, the total energy is equal to 0. Nothing's happening. We haven't pushed it back and had any compressed energy. There's no elastic potential energy. There's no kinetic energy. It's not moving. Position B, we're holding it in place. We have a lot of potential energy stored up there in terms of elastic potential energy. Position C, we have a combination of energy. We have a total energy value of both kinetic energy and elastic potential energy. And you can probably guess what questions like this are headed. What velocity does the object maintain at position C? We can figure out our velocity at position C by setting our energy at position B equal to our energy at position C. Just like we did before, expand out all the energies that are possible and eliminate the ones that don't apply in each situation. We have only elastic potential energy at position B. We have a combination of kinetic and elastic potential energy at position C. We can set them equal to each other, expand them out, and solve for variables such as velocity and whatnot. Finally, Unit 4, Energy, ends with this topic called work. We've talked about work at the beginning of this. Work is your force applied in a particular situation multiplied to your distance on which that force was applied. Anytime you get one of these relationships, you can see how it kind of mirrors our y equals mx that we've talked about. You can therefore build xy plotted axes which describe this system. Force being on the x-axis perhaps, distance certainly being on the y-axis. And anytime you get one of these graphs, the shaded area beneath the curve is equal to the amount of work performed. Shaded area. So you can expect to see questions whereby you're tasked with solving for what's the amount of work performed based on force and distance values, even if it's a variable force. Finally, this unit ends with an equation, the work kinetic energy theorem, which states that the amount of work performed in a given situation is equal to the change in kinetic energy. Change in kinetic energy. Expanded out, this equation looks like this. Situations that use the work kinetic energy theorem are varied, but a lot of them comes down to, hey, we're applying a force to a system. So, I don't know, the simplest term that I can think of is, or the type that I can think of is a man pushing a box. Applying a net force to a box. Even if it's a complicated question, you have to resolve out frictional forces and all sorts of stuff like that. We're applying, you can do all that and figure out what your net force is. We're applying a force over a given amount of distance. What sort of velocity do you have at the end of that motion? Well, you can solve out your net force. You have your distance that you're working it with. Routinely, you might have an initial velocity, but frequently you don't have an initial velocity. A lot of these break down into one of these components goes to 0, whether it's you start from rest or you go to rest or whatnot, one of those may be 0 and that frequently, and that makes the rest of the workup pretty easily, because then you can just isolate and solve for whatever necessary variable. Unit 4.